in 3. And the form of the differential equation, in general, it is written as a0 d raised to n y by dx raised to n. So a0 is the coefficient and it is the nth order derivative, and a0 is constant. We are writing it in generalized form, plus a1 d raised to n minus 1 y by dx raised to n minus 1 plus etc. Then you will have a n minus 1 dy by dx plus an into y is equal to capital X, is the form of the linear differential equation of higher order constant coefficients. But instead of every time writing this d raised to n y by dx raised to n, they have preferred a notation. They define the operator called as capital D, and capital D operator, they define it as d by dx, that is a derivative with respect to x. Of course, when we say d square, it is going to be d operating on d, so it is going to be d by dx of d by dx of something. So it is nothing but d2y by dx square. That's the notation they are going to follow. And so obviously we can go ahead and think of what is d raised to minus 1, because if it is rather raised to minus 1, we should say it as d inverse, and d inverse means 1 upon d is nothing but integration. Just remember it for the time being. Capital X is any function of x. It cannot contain y. That's why they write it as capital X. And so when I try to rewrite this differential equation, it will be a0 d raised to n y. So it is d raised to n by dx raised to n of y plus a1 d raised to n minus 1 y plus etc. plus a n minus 1 plus a n y equal to capital X. This gives us a benefit to define altogether a new operator, which is a0 d raised to n plus a1 d raised to n minus 1 plus etc. plus an minus 1 d plus an, this whole thing operating on y equal to capital X. And then they say it is nothing but some function of d operating on y is capital X, is the form of linear differential equation, with the condition that this f of d must be polynomial in d. In short, it also means that it cannot contain the functions like sin d, cos d, e raised to d, वगैरह वगैरह. It has to be strictly the polynomial in d. And capital X is any function in small x, of course. So we have the form f of d operating on y equal to capital X, linear differential equation. Being a polynomial in d, coefficients can be constants, and they are constants here. So this notation is valid. Any doubt in this? Simple concept. This is the form useful for your online exam. What is the general form of differential equation? They can always say it is f of d operating on y equal to phi of x, phi of small x, means any function, where f is polynomial and phi is any function. Notation can vary, right? Now, before we proceed further with the solution part of it, let us solve some equation which is very simple. d2y by dx square equal to e raised to 2x, which is the second order differential equation. It is a linear differential equation. It has got coefficient as 1. There is no term of dy by dx. There is no y involved. Fine. This equation is solvable for us because it will be simply integration. So you integrate it once, it is dy by dx equal to integration of e raised to ax is e raised to ax upon a. So integration of e raised to 2x will be e raised to 2x upon 2 plus the constant of integration. So here for the diploma students, the formula for the first time, integration of e raised to ax is e raised to ax upon a. And then we integrate once again, so y equal to e raised to 2x, original half is there and again upon 2. Integration of constant is constant in 2x and one more constant of integration c2. So for diploma students, one more formula, integration of dx is x. Of course, when we are writing this formula of indefinite integration, there will be always constant involved into it when we remember the formula. So far so good. There should not be any difficulty for the regular engineering students. Fine. So I have got two parts. One is the one which involves arbitrary constants and other is just the integration. Nothing more than that. If we try to solve one more problem of the similar type, dy by dx, d2y by dx square equal to, say, sine of 4x plus x cube. What's so difficult into it? Integrate it. dy by dx, integration of sine is minus cos, so minus cos 4x upon 4 plus integration of x cube is x raised to 4 upon 4 plus constant of integration c1. So we have one more formula for diploma students. Integration of ax dx is minus cos ax upon a. Integration of x raised to n dx is x raised to n plus 1 upon n plus 1. Integrate it once again. So it will be y equal to minus 1 by 4 is already there. Cos x integration is sine 4x upon 4. 1 by 4 is already there. X raised to 4 is integrated as x raised to 5 by 5 plus c1x plus c2. Now, why I have taken these two examples is because it again contains a part which is quite similar in the first case, or rather exactly the same, which may lead to a conclusion that order is 2, so there is always two constants involved in the solution, and there is always a part in the solution which is going to be just the integration of the right hand side. Right? There was no dy by dx term, so the things were simple here. Probably they may become complicated. But from here itself, they say that we are going to solve, suppose, forget this right hand side, I have only d2y by dx square as 0. What will be the solution? Because again, solution will have this c1x plus c2 into it. Yes, because you are required to integrate it twice. And when 0 is integrated twice, it will still remain 0. So what solution we will have here? It will be y equal to c1x plus c2, which is a typical case when the right hand side is totally 0. So they define this particular part as what is known as the complementary function CF. And that is where this unit will start. We just say that we are talking of only those differential equations where there is no function of x on the right hand side. It is simply 0. And in that case, solution will be only complementary function. That integration part does not come into picture because the right hand side itself is 0. Right? And so, how are we going to get this? Is there any way, simple way to solve it? The course begins with stating the formulae for finding the complementary functions only. Having the knowledge of differential equations in M2, we can very well find out how those terms are actually obtainable. And also we require some knowledge of complex numbers while solving them. Okay. See, any doubt in this, I suppose, should not be. Right hand side does not mean anything so far as the constant portion is concerned. That is complementary function. The other portion is specifically integration. We will be referring to it as particular integral. Two parts of the solution. Solution will always have particular integral plus complementary function. Complementary function plus particular integral. So, linear differential equations of higher order with constant coefficients will have solution as y equal to cf plus pi. Cf only arbitrary constants, pi only the integration. Now when you use that term particular integral, this particular constant which we get in the indefinite integration does not come into picture. That's why it is particular integral. Constant has been taken care of separately. Right? So, methods for finding complementary function. So for CF, what is the form of the equation? It is f of d operating on y equal to 0, which is called as the auxiliary equation. This is not the given differential equation, right? We are just equating it to 0 and saying that solution of this will give us complementary function. Now, if this is equal to 0, now this is something which we are very difficult to understand. So f of d equal to 0. What is f of d? It is polynomial in d of degree n in general. So if f of d, which is polynomial in d, is equal to 0, it is bound to have n roots. So fd, if this has got degree n, then will have n roots, and these roots could be real, these roots could be complex. And how to solve such type of differential equations? Again we have learned it back where complex numbers, De Moivre's theorem, where we had some d raised to 7, rather x raised to 7 minus 1 equal to 0. So x raised to 7 is 1, which is written as e raised to I0, which is equal to e raised to I into bracket 0 plus 2n pi. And so x is equal to e raised to I 2n pi by 7, where n takes values from 0, 1, 2, 3, 4 up to 6. And you substitute those values and you will be getting 7 roots. You won't require it because we will be giving some standard formulae by which most of the equations can be solved. There will be hardly a case where we will be getting the terms of the order f of d can be of the order of 5 or 6. Mostly it will be up to cube, 4th power. They are happy. We will be getting 4 constants. But otherwise all those equations can be solvable. So here we are going to have n roots. Now very basic concept which otherwise will stick to any mathematical student in mind, as you are equating operator to 0, how is it possible? But we are engineering students, so we are least bothered about it. We should be least bothered about it, because then the entire thing will change. For simplicity, I will just take one differential equation, which is dy by dx minus my is equal to 0. Now this differential equation you have definitely studied, because it is the linear differential equation of the first order, first degree part of your maths, called as the linear differential equation. At that time it was type 5, very basic part, right? And we used to have integrating factor, which is the general form over there was dy by dx plus py equal to q, where p and q are functions of x, and integrating factor is e raised to integral p dx, and solution is if into y equal to integral if into q dx plus c. That plus c won't come into picture, we'll see how it has to be dealt with. So this is a linear differential equation. We will write it as d minus m operating on y equal to 0, and therefore d minus m equal to 0, and so d is equal to m. So far so good. We are following the procedure which is stated over here. Now what was the solution over there? It was dy by dx plus py is equal to q. Integrating factor, is it e raised to integral p dx? Yes. Solution, it was if into y equal to integral if into q dx plus c. Now if we just apply the formula over here, if is going to be e raised to integral minus m dx, because p is minus m, and so it is going to be e raised to minus mx. Right. Solution, e raised to minus mx into y, if into y, equal to integral e raised to minus mx, q in this case is 0, dx plus constant, right? And so it is e raised to minus mx into y equal to constant, which tells us y equal to c e raised to mx. I know. So what we have got over here, as per our solution, it is e raised to minus mx into y equal to integral e raised to minus mx into q 0 dx plus constant. So e raised to minus mx into y equal to constant, y equal to c e raised to mx. So far so good. Any doubt? Now suppose I have something like d minus m1 into d minus m2 operating on y equal to 0. Now as per our formula, we will be finding values of m, values of d when we solve this differential equation. So we will be getting d equal to m1, d equal to m2. For d minus m, if it is c e raised to mx, for d minus m1 it will be c e raised to m1x, d minus m2 it will be c e raised to m2x, but those two constants could be different. So they say that the CF will be c1 e raised to m1x plus c2 e raised to m2x. How? Matlab, this has to be substituted here and again operated. We just go with our mathematical induction. Could be wrong at times, but I am proving it for 1 and I am generalizing it for n. The second step for k equal to something, n minus 1, I am not doing that. Right? But that's where our engineering mathematics works. So we say that f of d equal to 0 has n roots, say m1, m2, m3, etc. up to mn, then CF is going to be c1 e raised to m1x plus c2 e raised to m2x plus etc. plus cn e raised to mn x, our formula number 1. When these are all real roots, it is just the generalization of the formula. Formula number 1 for finding CF. So we need to find roots of f of d equal to 0. Formula 2, we can now very well speed up. Say roots are real and repeated. In that case, part 1, suppose m1 occurs twice. So if the same root occurs twice, then you cannot write c1 e raised to m1x plus c2 e raised to m1x. No. This is for real as well as distinct. There should not be any repetition. Then this generalization works. If you have roots as 2 and 2, then it doesn't work. Because then that integration takes a different form. There is a cancellation because that will be implemented in Q. So the formula, they say that it is going to be CF for these two roots. It is C1 plus C2x e raised to m1x. And again they go for generalization, saying that if m1 occurs 3 times, then CF is going to be C1 plus C2x plus C3x square e raised to m1x, and you can generalize. So for real distinct we have formula 1, for real repeated formula 2, we will have 2 more formulae for complex distincts, complex repeated, and there will be only 4 formulae for finding CF. All the problems in unit 1, you will have to find complementary function. You will not be given any marks for finding complementary function, but if you miss out complementary function, if that is wrong, solution is wrong and you will be given 0. So I have done complementary function, so I should get at least 2 marks. No, you should be doing complementary function. I know only particular integral, I have made some mistake in CF, you will get 0. CF has to be correct, right? Only 4 formulae. Of course, we are required to solve the polynomial equation and find the roots. 3. Method number 3 for finding CF. It is going to talk about the complex roots. Roots are complex and distinct. Now again, for the benefit of diploma students, this will help you a lot, right? So I can increase my TRP in a way, because diploma students will very well, because I know what you don't know. That's the fun of it. Complex roots. What is a complex number? It is the number which involves I. What is I? Whose square is -1. Otherwise, no real entity can have square. Matlab, if you have anything as a square, it will be always positive, whether a is positive or negative. Only in case when a is complex, it can be negative entity. And that's why it is called as imaginary. That's why that I. So complex roots, for example, something like x square equal to -4. So you cannot find x. In that case, we write it as x equal to plus or minus 2i. Right? This is complex number. Now complex number in general is written as alpha plus or minus I beta, where alpha is called as a real part and beta is called as imaginary part. And in our last unit, when we again talk about complex integration, over there this will be playing a dominant role. It will be just the extension of Argand diagram that we have studied earlier. Okay, so these are the complex roots. How many roots are these? 2. What is our formula says? What are we talking about right from the beginning? For every root there will be one constant. So if these are 2 roots, and I am saying roots are complex and distinct, say alpha plus or minus I beta, then CF is given by e raised to alpha x, that is e raised to real part into x, into bracket c1 cos beta x plus c2 x. And I don't think that this could be a difficult task to understand, because in complex number we used to represent it as e raised to I something, I theta, r e raised to I theta. Right? So it is quite similar to that. But there is no I involved in this. So the solution is a real one. They have gathered the real part. See, it is alpha plus I beta and alpha minus I beta. So e raised to alpha, if we go with our standard notation, e raised to alpha plus I beta, as per our earlier notation, there are two roots, right? Alpha minus I beta. This should have been the formula. That is our formula 1, real distinct. So we are just extending it to this. Now what happens is, I can collect C1 e raised to alpha x, rather I can collect e raised to alpha x common and write it as C1 e raised to I beta plus C2 e raised to minus I beta. Is it acceptable to everybody? Should be, because e raised to alpha plus I beta into x, alpha minus I beta into x, C1 e raised to m1 x plus C2 e raised to m2 x. So e raised to alpha x taken common, it is C1 e raised to I beta plus C2 e raised to minus I beta. So this is going to be C1 cos beta x plus C2 sin beta x, C2 sin beta, C1 cos beta x plus I C1 sin beta x plus C2 cos beta x minus I C2 sin beta x. So I will collect the terms of cos beta x, that will be C1 plus C2, which is named as C1, and I into C1 minus C2, which is named as C2. So we don't use, even if somebody uses this formula, nothing is wrong. But our book specifies this formula, which can be very well derived from formula 1. So these are complex and distinct roots, and formula 4, it will be complex and repeated. And so there will be again two parts, say alpha plus or minus I beta occur twice. So twice means alpha plus or minus I beta themselves are two roots and occurring twice, so 4 roots. In that case, CF is going to be e raised to alpha x into bracket C1 plus C2x cos beta x plus C3 plus C4x sin beta x. That will be the formula for complex repeated when occurring twice, and if it occurs 3 times, alpha plus or minus I beta 3 times, then CF is going to be e raised to alpha x into bracket 3 times means 6 constants, C1 plus C2x plus C3x square cos beta x plus C4 plus C5x plus C6x square sin beta x. And where we complete our first part, most essential for online exam, you will be getting something, because you will have to find the roots and tell me the CF only. There are so many online problems which are based on only CF, right? What is important over here is nothing from M3, nothing from integration, just these 4 formulae, and you should know how to solve a polynomial. Sometimes people feel, how are we going to get these complex roots in the repeated form? Because we haven't started with any problems yet. So that is very simple, because they will give us the equation in that form. If they talk about something like d square plus 4 bracket cube operating on y equal to 0. So either they will give you exact cube of it. The original equation could be in the form, if you can make the cube of it, it is going to be d raised to 6 plus 3 times d raised to 4 into 4, right? So it is going to be 12 d raised to 4 plus 3 times 4 square, so 16 into 4, 16 into 3, 48 d square plus 64 operating on y equal to 0. That's why one should be very clever in solving the equation, because this doesn't seem to be a perfect cube to us. But this will reduce to this, and ultimately you will say, therefore d square plus 4 is equal to 0, a bracket cube equal to 0. That means d square plus 4 equal to 0, d square plus 4 equal to 0, d square plus 4 equal to 0. That means 3 times. Okay, so you will have d square equal to minus 4 3 times, and so d equal to plus or minus 2i 3 times. So alpha equal to 0, beta equal to 2. Use the formula. Nothing more than that. So it is possible. So even its square can be possible. It can be d square plus 1. It can be d square plus a square. D square plus a square will be easy to imagine, because you can see that 3 clearly. Because it is a number, it is a big trouble to us, right? And never mind, over here it can be even d square plus 3 also. In that case it is going to be plus or minus I root 3. So let it be root 3. It may not be the exact value, right? So this is where we will stop, and from tomorrow, from next lecture, we will first of all solve all the problems related to CF. Okay, we'll practice that, all the complicated. There are 1 or 2 problems where practically nobody can imagine what are going to be the roots, but that's the worst case. In those 2 problems we will just mark it ke ha nahi yaar, if you cannot get CF only, then don't proceed to PI, right? But only 2 problems. See, if somebody gives you a square of something like d square plus 5d plus 2, if he actually squares it and gives it to you, there are no other factors, so this cannot be factorized. If this would have been d square plus 5d plus 4, so it can be d plus 4, d plus 1. So at least you can get that factor. But if it is something like 3 or 2, you cannot factorize this itself, and then 3 terms and their square, you should be getting it equivalent to this and saying that this is equal to 0 twice, and then find the roots and go further. So those type of problems, difficult. There is no technique also. We have got synthetic division only for the first order root, not the second order. Okay, but otherwise the problems are simple.